Sorry about this, everyone. I will be more organized on Wednesday. Okay. All right. So last time we started talking about partial derivatives. And we saw that, so for functions of two variables, we have now two variables that we're allowed to change. So for functions of one variable, there we go. So if we have a function of one variable, f of x, then the partial derivative of f at a is going to be the rate of change. Wow, this is still really simple. Of f with respect to x at x equals a. So in other words, if we're at x equals a and we change our x value by just a little bit, how is the function changing as we change x by a little bit? Well, for functions of two variables, okay, nope, that's not what I wanted to do. For functions of two variables, we have now two variables that we're allowed to change. I apologize. Let me. Right. Oh, there we go. That works. Okay. For functions of two variables, we now have two variables we're allowed to change by a little bit. So f of x, y. And so we're allowed to leave one of the variables fixed, change the other by a tiny bit, and see how the function changes. So for instance, we saw yesterday for heat index is a function of temperature and humidity. And so if we're at a specific temperature and humidity, say 90 degrees and 50% humidity, suppose we leave the temperature fixed, but change the humidity by just a tiny bit, what's going to happen to the function? Well, that's what the partial derivative of the heat index with respect to humidity tells us. So functions of two variables, we have two partial derivatives. We have the partial with respect to x, or whatever we call the variables. So the partial with respect to x at the point AB is limit as h goes to 0, f of, so we're changing the x value a tiny bit. Oops. Great. How do I end it? That's fine. I can make that work. Up here. So we're changing the x value by a tiny bit, looking at how the function changes. So this is the change in the function, and then dividing by how much we changed the x value by, but we're leaving the y value fixed. And this is the partial with respect to x at point AB. And then we can do the same thing for the partial with respect to y. And that's the same thing, except now we're leaving the x value fixed and changing y by a tiny bit, seeing how the function changes, and then dividing by how much we change y by. So the rate of change with respect to y. So f of a b plus a tiny bit minus f of ab, so change in our function when we change y by a little bit, divided by how much we changed it by. and then take the limit as h goes to 0. Okay. So that's good to know the definition of the partial derivatives, but that's not actually how we're going to be calculating these, because as you probably remember, taking those limits generally kind of sucks. Not the easiest way to do these things. Luckily, we already know exactly how to calculate these partial derivatives. Everything you need to know to calculate these, you learned already in 140 and 141. So here's how we calculate partial derivatives. I wish I could make this bigger. Okay. Okay, so basically, when we want to calculate the partial with respect to x, and just as a reminder, another way of writing the partial with respect to x is df dx, except now we're using these fancy d's here, these cursed d's, instead of the regular d. So we use these when we're talking about normal derivatives for functions of one variable. But for partial derivatives, we use these cursive d's just to indicate that it's a partial derivative. Because now we have two variables we can take derivatives of, and it's just it's a notation thing. You're likely not going to get points taken off on an exam for mixing those up, but it's good to get in the habit of doing the fancy d's for the partial derivatives. Okay, so the way we actually calculate these is you look at your function, wherever you see y, you're going to treat it as a constant. So remember, for the partial with respect to x, we're fixing y. So now we're treating that as a constant. So treat y as a constant, and apparently my internet connection is unstable. Awesome. So treat y as a constant. And then you're just going to use your 140 and 141 rules to differentiate as usual with respect to x. Differentiate as usual with respect to x. Does that make sense to everyone? So if we look at a function of two variables, we're going to see stuff involving x and y. Wherever you see y, now y is, mentally you're going to think of y as a constant. So now the only variable is x. So now it's just a function of one variable. You differentiate as you normally would a function of one variable. So what about sine xy? Okay, cool, let's do sine xy. Well, let's do something a little more simple, and then we'll do sine xy after that. Okay, so for example, suppose we had a nice simple polynomial function. So f of xy is going to be x cubed plus x squared y cubed minus 2y squared. Let's calculate the partial with respect to x at 2, 1, and the partial with respect to y at 2, 1. Wow, okay. I really wish I knew how to erase. I'm going to figure this out as soon as we are done with this today. I thought it would be more obvious. Okay. So we're going to calculate the partial with respect to x and the partial with respect to y at 2, 1. Okay, yeah, and I guess I forgot to mention, for the partial with respect to y, we do the opposite. Now, for the partial with respect to y, we treat x as a constant, differentiate as we usually would for a function of y. Okay. Okay, so first step. We want to calculate the partial with respect to x at 2, 1, so we just need to take the partial with respect to x without plugging in 2, 1. So we're looking at this function. Wherever we see y, we're thinking of it as a constant now. So it's just a function of x. We're differentiating with respect to x. What happens to our function? So almost gave it away. So x cubed, the x cubed term, if we treat y as a constant, differentiate with respect to x, what happens to x cubed?
3x squared.
Oh, someone's got their mic going. Good job, whoever just answered. For some reason, I didn't see that. Yes, exactly, 3x squared. So x cubed becomes 3x squared. Oh, come on, go away. Go away. Okay, well, there we go. No? Okay. How about the x squared y cubed part? So y cubed we're treating as a constant. X squared y cubed becomes, so the x squared becomes 2x, y cubed is just a constant, so that hangs around. So that becomes 2x y cubed. And how about the minus 2y squared part? It becomes 0 because it's just a constant as far as we're concerned. So plus 0, which you don't necessarily know, right? But we'll just do it just to emphasize it. So then the partial with respect to x at 2, 1. Now wherever we see x, we plug in 2. Wherever we see y, we plug in 1. So 3x squared becomes 3 times 2 squared. 2xy cubed becomes 2. X becomes 2. Y becomes 1 cubed plus 0. And so we get 3 times 4 plus 4. So we get 16 for the partial with respect to x at the point 2. Make sense? It's a really easy process once you train your brain to treat one of the constants as, one of the variables as a constant. So let's do the same for the partial with respect to y at 2, 1 real quick. Okay. So now we're treating x as a constant, which is mentally, for a lot of people at first, more difficult than treating the y as a constant, but we're treating x as a constant now and differentiating as if it were just a function of just y. So the x cubed becomes what? 0, it's just a constant now. The x squared y cubed becomes what? Careful. Well, close, yes. So the x squared is just a constant, so that hangs around. The y cubed becomes 3y squared, so we get 3x squared y squared. So 3x squared y squared, or if you like, just x squared times 3y squared works also. And then what happens to the minus 2y squared? That becomes minus 4y, correct. So minus 4y. And so then calculating the partial with respect to y at 2, 1, plug in x equals 2, y equals 1. We get 0 plus 3 times x becomes 2. So 2 squared times 1 squared minus 4 times 2. So we get 12 minus, times 1, sorry. So we get 12 minus 4. which is, of course, 8. Okay. So you literally already know how to calculate the partial of pretty much almost every function. It's just a matter of going through the mental process of treating one of the variables as a constant and then just using all the normal rules you already learned from 140 and 141 to take the derivatives as a function of the other variable. Okay, so someone mentioned, what about sine of xy? I heard a noise. Probably just me doing that. Okay. So suppose our function is sine of xy. Let's just calculate the partials. With respect to x and the partials with respect to y. Okay, so for the partial with respect to x, we're treating y as a constant, differentiating as a function of x. So if we had, say, sine of 2x, we're multiplying x by a constant. What is the derivative of sine of 2x with respect to x? So we'd have to use the chain rule. Sine becomes what? Sine becomes cos. So we get cosine of what's inside. But then you have to multiply that by the derivative of the inside. Sorry, we're jumping the gun here. But yeah, cosine of 2x, and then you have to multiply by the derivative of the inside. Sorry, we're still treating it as sine of 2x. So sine of 2x, sine becomes cos, and then you have to multiply by the derivative of the inside 2x, which is what? 2, right. So for a sine of 2x, it would become 2 times sine of 2x. But now instead of 2, our constant is just y. So we do the same process. Sine becomes cos. So it's cos of xy times the derivative of the inside. So y is a constant. Xy becomes what when we differentiate with respect to x? Y, exactly. So the partial with respect to x is just y times cos of xy. Because that xy works just like you're multiplying x by a constant. And it's the same process. So now let's do the partial with respect to y. Now we're treating x as a constant. And let's differentiate as we would. So sine becomes, once again, cosine of the inside, xy. Now the inside is xy, but now x is a constant. So it's some constant times y. When you differentiate with respect to y, you just get a constant, x, right? So we get x cos xy. Everyone understand what's going on with that one? These are really, really, really easy after you've done a couple of them. It just becomes second nature. Is there ever a case where you take the derivative with respect to x and y at the same time? Not exactly. When we talk about directional derivatives, there's kind of a way to do something like that. So you're taking the derivative a little with respect to x and a little with respect to y. So like 50% with respect to x and 50% with respect to y, or like 20% with respect to x and 80% with respect to y. That's not really how we think of it, but there is sort of a way to do that. And when we talk about directional derivatives, that's essentially kind of what we're doing. But as far as you're concerned, no, not yet. We'll get to that though. And then just for practice, Let's do one more, say, slightly complicated example. Let's see. So let's say we have e to the power x over 1 plus y. Is it clear what I mean here? So this x over 1 plus y is the power of e. So it's e raised to that power. So let's just calculate f sub y for some quick practice. And I promise I will figure out how to erase stuff. Okay. So we're taking the partial with respect to y. So we're treating x as a constant, differentiating with respect to y. And so let's do this example. So we have e to the power of something. And so we have to do the chain rule here. So e raised to, so when you differentiate e to the power of something, what happens to e? So for just like e to the y, what happens when you take the derivative? Right, so you would just get e to whatever the power was. So that's the derivative of the outside part. So e to the same power, x over 1 plus y. And then now we need to take the derivative of the inside. So x over 1 plus y, when we treat x as a constant, differentiate with respect to y, what happens? See if people are able to format this. Exactly. Yes. So you could do the quotient rule, or you could do a chain rule, or however you like. But what we end up with is, so the x, you can just pull that out. So it's like x is a constant times 1 over 1 plus y. So you get the x. And then the 1 over 1 plus y, you can think of it as x times 1 plus y to the negative 1 power. Whoa. There we go. So this x hangs around because it's a constant. 1 plus y to the negative 1 becomes negative 1 plus y to the negative 2, which is so negative 1 over 1 plus y squared. And so, so yeah, this is e to the x over 1 plus y times negative x over 1 plus y squared. Exactly. So really none of these are difficult. They're just, some take a little more work than others, but taking partial derivatives, very easy. Any questions before we move on? Okay, cool. Okay, so let me talk briefly about sort of the geometric interpretation of the partial derivative. And here's a time where it would be nice if I were a better artist, but I'm going to do the best that I can here. So the interpretation of our partial derivatives. or as I call them, just partials. Commonly referred to as just partials rather than partial derivatives, just for simplicity. Okay, so suppose we have a function f of xy. Let's look at the graph of f of xy. So we have a function of two variables. The graph of a function of two variables is going to be a surface in R3. Okay, so suppose this is a graph of f of xy here. Okay, so let's pick, suppose we want to look at what the partial with respect to x at some point AB is, and the partial with respect to y at the same point AB. So let's look at the point on the graph where x is A and y is B. So that's going to be the point A, B, and the graph is z equals f of xy. So z is going to be f of AB. So that's our point. Okay, so this graph of our function is a surface. Pretend you're at this point here, and this surface is just like a hill or something, and you're walking along this surface. Okay, so the way we're going to think of the partials with respect to x and with respect to y are as follows. So the partial with respect to x. So you're at the point AB. So walk along the surface in the x direction. So walk in the positive x direction. At the point here. So here, this is the positive x direction. So from here, we're going to walk in this direction. So notice when you're walking in the positive x direction, does it look like you're going downhill or uphill? It looks like we're going downhill in this case. Okay, so if you're walking in the positive x direction, at this point, the partial with respect to x is just going to be the slope, essentially. What's a better way to put that? Yeah, it's essentially just going to be the slope of the surface as you walk in this direction at the point. So the slope is just going to be, and if you're walking in the positive x direction, you're going to trace out some curve, this guy here, and then the slope is just going to be the tangent, the slope of the tangent line at that curve at the point AB. So here we're walking downhill at AB when we go in the positive x direction. So the slope is going to be negative. So the partial derivative is going to be negative of something. And it looks like it's fairly steep. So it's going to be negative a large number. Does that sort of make sense? So if you're walking on a hill, you can walk north. So you can walk, I guess in this case, so south would be like towards the positive x direction. East would be in the positive y direction. So when you walk south, you happen to be going downhill. And how steep you're going downhill is the slope. And so the partial with respect to x at that point is going to be the slope, so it's going to be negative whatever at that point because you're going downhill. Do we have a tangent line or a tangent plane? So the way to think of it is, so start at AB. When you walk in the positive x direction, you're tracing out a curve on your surface. And let me see if I can draw a better picture here. So you're at this point. X, Y, Z. So you're walking in the positive x direction. You're tracing out a curve. So that's a curve. And so at the point AB, if you look at the tangent line to the curve, so it's, yeah, you kind of have to like put it in 2 dimensions to do that. So maybe that's a little weird. But just think about it as the steepness of the path at that point. So you can be going uphill or downhill, that's positive or negative. And how steep it is how big the number is. Okay, so that's the partial with respect. Sorry, does that answer the question? It's a little difficult for me to put in words. Okay. What if you go in the y direction? Well, good question. If you go in the y direction, so you're walking in the y direction. So it looks like when we're walking in the y direction, okay. So when you walk in the x direction, this the steepness is the partial with respect to x. And when you walk in the positive y direction, the steepness is the partial with respect to y. Exact same thing happens there. So it looks like when we walk in the y direction, if I drew it correctly, we're kind of not going up or down. We're sort of keeping the same height as we walk in the y direction, sort of. And so the partial with respect to y, if it's how I drew it, would be 0. But that's not a great drawing. Let me see if the book has. The book, of course, has a better picture, I'm sure. Let's see. Okay, can everyone see? For some reason, I can't see this, but can everyone see the scan of the book? Cool. Okay. All right, so here's what you want to be thinking. So here, this is our surface here. When you're walking in the positive x direction at this point, you're going downhill. And so you're tracing out some curve. And so the slope of that guy is going to be the partial with respect to x at that point. Similarly, if you're walking in the positive y direction, you're going to be tracing out a curve. In this case, you're also going to be going downhill. But the partial with respect to y at that point is going to be the slope of the hill at that point. You're going downhill, so it's going to be negative, and it looks pretty steep, so it's going to be a large negative number. But that's the geometric interpretation of the partial derivative. Once again, not super duper important, but it's good to understand what's going on. Nope. Hang on. And I've lost you again. I apologize. I don't know what happens to Zoom every time I do this. No, I don't. There we go. Whiteboard. Okay, excellent. All right. Okay. So, where are we? Okay. So let's look real quickly at implicit differentiation. What? No. So implicit partial differentiation. So you foolishly probably thought implicit differentiation went away with Math 140. Unfortunately, it did not. We can also do implicit differentiation for functions of two variables, but it's not difficult. So suppose z is defined implicitly as a function of x and y. So for those of you who probably, many of you who probably cannot read that, that says, suppose z is defined implicitly as a function of x and y. So what does it mean to be defined implicitly? So that means you have some equation involving x, y, and z, but we're only allowed to change x and y. And that equation is satisfied for some x and some y for certain values of z. So for instance, suppose we had the equation. So basically, so when z is defined explicitly as a function of x and y, let me write it this way. Explicit. So if I get z by itself and get all the x and y on the other side, then I say z is defined explicitly as a function of x and y. So if I had z is like x squared plus y squared, I have z by itself. When I change x and y, I know exactly what z is. If I have some equation where I cannot get z by itself, then I would say z is defined implicitly as a function of x and y. So for example, if I had, let's say, x cubed plus y cubed plus c cubed plus 6xyz equals 3. So this is an equation involving x, y, and z. X and y are my independent variables. Those are the things I'm allowed to change. And for some value of x and some value of y, there are some values of z that work to satisfy this equation. So when you define an x and a y, this tells you what z has to be. But you're not able to get z by itself in this case. There could be multiple values of z that work for this, but yeah. Does that make sense? So just like when you define y implicitly as a function of x and y, you have some equation involving x and y. X is still your variable, your independent variable, and y depends on x, but you can't get y by itself. So here, we're thinking of z as a function of x and y. But unfortunately, we can't get it in this form, where you can write out exactly what z is, get z by itself, write it in terms of x and y. But z is still a function of x and y, even though we can't get z by itself. So let me write that again. So we had our x cubed plus y cubed plus c cubed plus 6xyz equals 3. Let's look at the partial of, so z is a function of x and y, even though it's defined implicitly. So we can take the derivative of z with respect to x and the derivative of z with respect to y. So let's look at the partial with respect to of z with respect to x and the partial of z with respect to y. Oops. So let's find. We'll do the partial of z with respect to x, and it'll be the exact same process for the partial of z with respect to y. Okay, so we're going to do this like we did for partial differentiation for functions of one variable. Okay, so you're going to take the partial with respect to x of both sides. And so what we're going to do is take the partial with respect to x of both sides. So that means, remember, wherever you see y, you treat it as a constant, and you differentiate as usual with respect to x. The difference now is, now we also have z. So what do we do when we see z? So remember, z is not really its own independent variable. Z is a function of x and y. So we can take the partial of z with respect to x. So whenever you see z by itself, when you take the partial with respect to x, it just becomes the partial of z with respect to x. But then if we have z cubed, we're going to have to use a chain rule when we get to it. But we'll get to that in a second. Very quickly, let me go through this. Okay, so x cubed, when we take the partial with respect to x, what happens to x cubed? So careful, when we take the partial with respect to x, y is treated as a constant, and we differentiate as a function of x, so x cubed becomes 3x squared. What happens to y cubed? Treating y as a constant, it becomes 0. And now z cubed, so for z by itself, it would just become dz dx. But now it's z cubed, so you have to use the chain rule. So something cubed, when you take the derivative, it becomes 3 times something squared. So we get 3z squared times the derivative of the inside, z, which becomes dz dx. Does everyone see how that works? So we're using the chain rule here. Z cubed is just something cubed. Something cubed, when you take the derivative, becomes 3 times something squared. That's our 3z squared. Times the derivative of the inside. The derivative of z with respect to x is just dz dx. Does everyone see? That's how that works. Okay. And then we have plus 6xyz So now we have to use the product rule. So 6xyz. So we're treating y as a constant, 6 is also a constant. So 6y, we'll just write that out there just for simplicity. And then x times z. Both of these, we can take the derivative with respect to x, so we have to do the product rule. So it's 6y so derivative of x with respect to x times z plus x times the derivative of z with respect to x. So what's the derivative of x with respect to x? 1. So we get 1 times z. Let me move you over. Oh, good. Plus x. So derivative of x with respect to x times z plus x times the derivative of z with respect to x. So x times dz dx. So that's the left-hand side, and then we take the derivative of 3 with respect to x. What's the derivative of 3 with respect to x? Zero, exactly. That's a constant. Okay. And once again, wish I knew how to use this better. Oh, wait. Oh, cool. This was being covered up the whole time. Awesome. Wish I'd seen that. Okay, so we have, so now what we want, I apologize for going over here a little bit. We want to figure out the partial of z with respect to x. And so we saw last time, we have partial with z with respect to x. We see it a few times. We basically just want to get that by itself now. So we're going to get dz dx by itself. So we had, let me rewrite it, 3x squared plus 0 plus 3z squared dz dx plus 6xy. I'm just sorry, 6xz. 6x. Sorry, yeah, I guess I cut out there. My internet cut out. I don't know what happened to the whiteboard. Awesome. But let's continue with this. I apologize. Okay, so we had, whoops, erase, undo. So we had 3x squared plus 0 plus 6xz plus, nope, not 6xz, 6yz plus 6x dz dx. Oh, and I forgot, of course, our 3z squared dz dx. That was the left-hand side equals 0. So we're just going to isolate dz dx. So dz dx, look at all the terms involving dz dx. So that's this guy and this guy. So that's dz dx times 3z squared plus 6x. Bring everything else over to the other side. So minus 3x squared from both sides minus 6yz. And then we just divide both sides by this. So divided by 3z squared plus 6x. 3z squared plus 6x. And so when we do that, we get dz dx is equal to negative 3x squared minus 6yz divided by three z squared plus 6x. And of course, you could simplify that if you want, but should it be 6xy? Yes, you're absolutely right. 6xy dz dx. You are correct. That was my fault. 6xy. Correct. Sorry. And so that's a partial with respect to x, of z with respect to x. So basically, I apologize for going over again. So, and it went away, but we had our function involving x, y, and z. You take the partial with respect to x of both sides. That works out normally, as long as it only involves x and y. You treat y as a constant, differentiate with respect to x. But wherever you see z, z becomes dz dx, and anything involving z, like z cubed, you have to use the chain rule. So you do all that, take the partial with respect to x of both sides, get dz dx by itself, and then solve for that. And that's how you do implicit differentiation. And if you want a dz dy, you do the same, but you take the partial with respect to y of both sides. Then you isolate dz dy, and that's how you would do that. Any questions about, did I just go out again? So it looks like the laptop is on, but my desktop is not. I apologize for this. This has just been a cluster. Okay, what is chat saying here? There we go. Now we're back. Okay. Okay, so let me see if I can see. Okay, so where did the minus 6yz come from? Let me address this one at a time. The minus 6yz comes from this guy here. So we want to get dz dx by itself. And so we're moving everything not involving dz dx over to the other side. So that's where the minus 3x squared and the minus 6yz come from. Does that answer your question? Okay, cool. Do we have a quiz on Wednesday? Yes, there's going to be a quiz on Wednesday. So I'm either gonna figure this out today, obviously, but I'm either gonna do a Canvas quiz, or that's probably the easiest way to do this. If I can figure out a nice, easy way to do a Canvas quiz, or maybe a WebAssign, it's probably going to be some online quiz. And office hours are regular time. Yes, so office hours, I'm just going to basically extend. So normally I would have office hours directly after the lecture. So I'm just going to extend this lecture for an hour or so, and we can do office hours like that. And I'll see if I can get the whiteboard working for you guys if you want to write stuff out and that kind of thing. But I'll keep this going for office hours. What I want to do is I want to finish lecture on this for maybe 10 minutes or so, just so the video be up if people aren't able to stay, because I want to finish partial differentiation today due to some technical problems. I wasn't able to get through as much as I wanted, but yeah. regular office hours. So Tuesday 1 to 2, Monday 10 to 11, or directly after class. And I'll create a meeting for office hours for Tuesdays. But yes. Yeah, so there's going to be a quiz on Wednesday. I'll probably make a Canvas quiz. If worst case scenario, no, that's how we're going to do it. Yeah. So the quizzes are probably going to be more difficult because obviously I can't keep you from doing them open book or that kind of thing. And I guess there's no problem with doing that as long as I make them more difficult. And you'll probably have more time, but they're not going to be during class time. I guess you'll probably just have a certain amount of time to do it, a certain window of time, and you can just do it. Then I'd rather just have class time to do lecture, because not a big fan of quiz time cutting into lecture time. Kind of annoying, but yeah. Okay. Any other questions? So I'm going to go ahead and really quickly finish up talking about partial derivatives. There's not too much to talk about. Not too much left. Okay, so we looked at partials for functions of 2 variables. Let's look at partials for functions of 3 variables. Or several variables. Let's look at it for 3. And the process is exactly the same for more than 3 variables. So for functions of 3 variables, now you have 3 variables, x, y, and z. And so we can take partial derivatives with respect to any one of those 3 variables. And so the process is exactly the same. So if you want to take the partial of f with respect to x, now you're going to treat y and z, the other 2 variables, as constants. And you're going to differentiate as usual with respect to x. So basically, it's the same process. When you take the partial with respect to a variable, you treat every other variable as a constant, differentiate as usual with respect to that one variable. It's the same thing for y, and then for the partial with respect to z, of course, you treat the other 2 variables, x and y, as constants. So as constants, and you differentiate with respect to z. So for example, if we had the function of 3 variables, natural log of z times e to the xy. Let's look at the partial with respect to x and the partial with respect to z. We could do the partial with respect to y, but the process is exactly the same. So the partial with respect to x. So we're treating we're treating y and z as constants, differentiating as usual with respect to x. So what happens to our function? So natural log of z we're treating as a constant, so natural log of z is a constant. E to the xy, treating y as a constant. So natural log z is a constant, so that just hangs around. E to the xy, so it's like e to the 2x, except instead of 2, it's y. So that becomes y e to the xy. Using the chain rule. Does everyone understand how that one works? I treated x, y, and z as constants, differentiated with respect to x and y. Sorry, with respect to x, sorry. And then that's what we get. what happens to when we take the partial with respect to z? So we treat x and y as constants. What happens? What do we get? Exactly. So e to the xy is now a constant because we're treating x and y as constants. Natural log z becomes 1 over z. So it's just 1 over z times that constant. So 1 over z e to the xy. Very easy. Okay, so one thing to be careful of here, though, is that notice now we have a function of x, y, and z. Before, I guess I erased it, unfortunately. We had an equation involving x, y, and z, but we said z was defined implicitly as a function of x and y. That's not the case here. Now z is its own independent variable. So we can take the partial with respect to z. So there's a subtle difference there, but you need to be careful that when you see something involving x, y, and z, that it's a function of x, y, and z, and not z defined implicitly as a function of x and y. Does anyone want me to say anything more on that? Can you do implicit with f of x, y, and z? You can, but then you need another variable to be implicitly defined as a function of x, y, and z. So you need like w or something. So you'd have some equation involving x, y, z, and then w. But then w is defined implicitly as a function of x, y, and z. So we can take the partial of w with respect to x, y, or z. And it's the same process as we did before. But you would need some other variable, which is defined implicitly in terms of those guys. Okay, and very quickly, I apologize, this is going longer than I intended. So we looked at partial derivatives. So just like with normal derivatives, you can take the second derivative, the third derivative, etc. We can take second partial derivatives, third partial derivatives, etc. So let's look at the second partial derivatives. Okay. So unlike with normal derivatives, there's only one second derivative, only one third derivative. With partial derivatives, we have multiple second derivatives. So a second partial derivative just means you're taking two partial derivatives. You're taking one partial derivative and then another. So we have 4 of them. And we write them as follows. So we have f sub xx. And this just means first we're taking the partial with respect to x. Then we're taking the partial again with respect to x. So we're taking the partial of our function with respect to x. That's one function of x and y. So we're treating this as functions of x and y here. And then we're taking the partial of that function, again, with respect to x. And another notation you might see is the d squared f over dx squared. But this is the more common notation here, f sub xx. So then we have 4 different orders we can take partials. So that's the first, f sub xx. Then of course we have f sub xy, which means first we take the partial with respect to x, and then we take the partial of that with respect to y. So first we're taking the partial with respect to x, and then we take the partial of that function with respect to y. And you could see this written as d squared f dy dx. And so this might be a little confusing because here we write f sub xy, and here we reverse the order. And so that is indeed a little confusing, but as we'll see in just a second, it's not actually something you need to worry about. And then, of course, the other partials are, of course, first we take the partial with respect to y, and then with respect to x. And then the other is, first we take the partial with respect to y, and then we take the partial again with respect to y. So those are the 4 second partial derivatives for functions of 2 variables. F sub xx, f sub xy, f sub yx, f sub yy. Okay. So very quickly, let's calculate the second partials for the following function. So we have xy squared. Nope, sorry. We're going to do a function we've already done here. Oh, that is right. So xy squared minus 3y. I guess we didn't do this one. So plus x cubed y. Okay. So let's calculate some second partials. We don't need to do all of them. Let's do f sub xx, f sub xy, and f sub yx. And f sub yy is going to work the same way. Okay. So in order to do the second partials, first we need to do the first partials. So this says take the partial with respect to x, and then take the partial again with respect to x. So first we need to take the partial with respect to x for that one. So the partial with respect to x, we're treating y as a constant. So xy squared becomes y squared. Minus 3y becomes 0. And then what happens to x cubed y? Right, we get 3x squared y. And then I'm going to do the same for the partial with respect to y because we're going to need to refer back to it later. So the partial with respect to y, we're treating x as a constant. So xy squared becomes 2xy. Minus 3y becomes minus 3. And then plus x cubed y just becomes plus x cubed. Okay. So now that we have those, we can calculate the second partials. So f sub xx, that means we're taking the partial with respect to x of the partial with respect to x. So we're taking the partial with respect to x and then taking the partial with respect to x again. The partial with respect to x we said was this y squared plus 3x squared y. Y squared plus 3x squared y. And when we take that partial, y squared becomes 0. And then the 3x squared y becomes 6xy. So that's f sub xx. F sub xy is, first we're taking the partial with respect to x. Then we're taking the partial of that with respect to y. So the partial with respect to x is that y squared plus 3x squared y. Then we take the partial of that with respect to y. The y squared becomes 2y. And then the 3x squared y becomes what? Anybody? Euler? it becomes 3x squared. Exactly. I'm sure not everyone is here. Okay. And then very quickly, f sub yx is, first we take the partial with respect to x, with respect to y, and then we take the partial with respect to x. So the partial with respect to x of f sub y, we said f sub y is 2xy minus 3 plus x cubed. So minus 3 plus x cubed. And we notice when we take the partial with respect to x there, we get 2y plus 3x squared. So notice f sub xy, in this case, happens to be the same as f sub yx. In this case, it didn't matter what order we took the partial derivative in. And in fact, that's always going to be the case for every function you're going to encounter in this class. And that's an important theorem that we'll refer to over and over. That's called Clairaut's theorem. So Clairaut's theorem is basically if you have a function of two variables, f of x, y, and I won't go over it, you can look at it in the book. If it satisfies some conditions that are always satisfied in this class, oh, come. Go away. Oh, come on, man. Go away. There we go. That's not the important part. The important part is that the mixed partials, f sub xy and f sub yx, are always the same. So you don't need to worry about those conditions. They're always going to be true in this class. The kicker, though, the important thing is that f sub xy is equal to f sub yx. Okay, so what about f sub zy and f sub yz? Well, that's not a terrible question. If f is a function of x, y, and z, the same thing is true there. Those mixed partials are going to be equal. So if you keep the same two variables, so f sub yz, y and z, it doesn't matter what order you take the derivative. F sub zy is going to be equal to f sub yz. F sub xz is going to be equal to f sub zx. F sub xy is going to be equal to f yx, etc. So it holds for those guys as well. And then finally, really quickly, so we saw we can take second derivatives by just taking one partial and then another partial. We can do third partials by taking one partial, then another partial, then another partial, so on and so forth. And we can, in fact, apply Clairaut's theorem for the higher partials to reorder the partials in whatever order we want to take them. So suppose I take the fourth partial, f sub xy xx. Clairaut's theorem says I can take them in any order I want. So that's the same. As long as I'm taking 3 x partials, 1 y partial, they're all going to be equal. That's the same as f sub y, then x, then x, and x, or f sub x, x, y, x, or f sub x, 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 y. Those are all the options here, but that's, you can reorder the partials in any order you want, and you're going to get the same answer. That's what Clairaut's theorem says. essentially. Any questions? Sorry for going just way over here, but I really wanted to finish this. So if you don't have any questions, I'm going to keep this going, and we will do virtual office hours. And I'm going to see if I can enable the whiteboard for everyone else. So let's see if I can do that.